Hello, I'm Dave Brown. In this program, we'll continue our study of directional control valves and complete the material covered in Chapter 8 of your text. Let's start by looking at basic valve design. Directional control valves must be adequately sealed, and we can obtain this sealing either with a shear action or by using a poppet valve. We can demonstrate what we mean by shear action with this cutaway. You can see that as we move the spool, these lands slide within the valve body, and when they are in the right position, they close off the desired passage by shearing off the airflow. There are four basic types of valves which use sliding or shear action elements: sliding plate or rotary disc, lapped spool, packed spool, and packed bore. This is what a sliding plate type valve looks like. This part here is referred to as a D-slide. As you can see, it slides against this mating surface and alternately connects and disconnects these passages here. In this position, outlet 1 is connected to the exhaust here, while the supply is connected to outlet 2. Here, the D-slide is positioned so that all valve ports are blocked. And finally, when we move the slide all the way over, outlet 1 is connected to the supply, while outlet 2 is connected to the exhaust. We can get the same type of shear action with what is called a rotary disc valve. Here is a disc from a typical rotary type valve. This particular one is intended for 3 positions, and the cutouts are located in the disc so that in the neutral position, all valve ports will be blocked. In fact, openings in the disc can be positioned to achieve all the standard valve center positions we covered earlier. Here is what a rotary disc valve looks like. These are the valve ports here on the base of the unit. And this lever here is used to position the disc within the valve. The sliding plate and rotary disc type valves have a number of advantages. First, because they have a sliding action, the valve mechanisms tend to wear in. This means they are capable of many trouble-free cycles even under adverse conditions. For example, they work well over a wide range of temperatures. They are virtually unaffected by lubricants or contaminants that might be in the air lines. And this type of valve tends to keep out foreign material from between the mating surfaces. You should note, however, that at high line pressures, large forces may be necessary to shift the valve slide, and the valve must be continuously lubricated in order to get maximum life from it. And if the pressure under the plate exceeds line pressure, the sealing member can be forced from its mating surface. So a sliding plate valve may not be suitable where such pressure conditions can occur. This is a packed spool valve. You can see the valve ports here and here, but the big difference you can't see until you look inside. Here is the spool from a packed spool valve, and you can see the resilient seals here and here. These seals slide snugly against the inside of the steel bore of the valve and provide an almost leak-proof seal. Because they come in contact with only a small area of the bore, these seals are less vulnerable to varnishing in place and need less maintenance than some of the other sliding types of valves. When necessary, the seals or spool can be replaced if the valve begins to leak. Also, this type of valve is less sensitive to contamination than the lapped spool type that we'll look at in a few moments. But there are other things to consider about packed spool valves. For example, Extreme temperatures may cause the seal to change size or become hard. If that happens, excessive leaking may occur. Also, you should know what kinds of airborne liquids might be in your system. The wrong combination of seal material and airborne liquid can cause the seals to swell, and the valve will require a higher shifting force. Here's another common type of directional control valve. It is called a packed bore valve because these stationary seals here and here are located in the bore of the valve. And you can see it doesn't take much effort to replace them. Just remove the worn seal like this, then drop the new one in place. This is the spool for a packed bore valve. It is steel on aluminum, and the land surfaces here and here have been made very smooth so as to minimize friction wear of the bore seals. When the spool is shifted back and forth, the lands fit tightly against the bore seals interconnecting the various valve ports. Just as with the packed spool valve, you should make sure the seal material will handle the kinds of airborne liquids that might be in your system without swelling. In fact, the packed bore valve and the packed spool valve have virtually the same characteristics. Just remember, packed spool valves are made with seals located on the spool, here, while packed bore valves have the seals located in the bore of the valve body, as you see here. Okay, the last type of shear action valve we're going to examine is what is called a lapped spool valve. This design depends on a close fit between ports to control the flow of air from one port to another. This is a lapped spool valve. You can see the valve ports along here. This illustration shows the main valve ports. Here's the valve body, and here are the flow passages. This one has 5 ports, which can be connected in several ways. All of the contacting surfaces along here are steel, and as you might suspect, in order to maintain a good seal, they must all be properly aligned. This is the spool, and you can see how nice and polished the land surfaces are. This means the valve is vulnerable to any foreign matter that might get between the moving parts. It could cause rapid wear and leakage, or even cause the valve to stick. However, if the air is kept very clean, this kind of valve can last a long time. The cost of lapped valves is higher than the other designs, and maintenance is generally more expensive. One problem you might look out for is varnishing. Because the parts fit tightly, oxidized airborne lubricants, such as from a compressor, may cause the parts to varnish in place. This happens most often after a long weekend, when the valves have been left idle. One last point. Watch what happens at the land edges as this spool is shifted. Because of the way in which they make contact with the bore, there is no crossover flow between ports when the spool moves. The open port closes before the next port opens. Packed bore and packed spool valves can also be designed to work this way. This feature greatly reduces the possibility of shift failure, which can be a problem if a valve is operating at low pressure, for example, in a pilot valve application. Okay then, you may encounter 4 types of shear action valves. Here they are again. The sliding plate or rotary disc, the packed spool, the packed bore, and the lapped spool. They all are suited for a wide range of pneumatic applications where a directional control valve is required. In certain cases, however, you may have special requirements. One such case occurs where the valve has to switch a high flow of air, or perhaps the system requires a very fast response. That's when a poppet valve might be used, and most manufacturers make it in a three-way model. It can handle high flows, gives good response time, and because of the design, it has less wear than shear action valves. Port A, here, is connected to the actuator. This is the exhaust port. And here is port P, which is connected to the system air supply. Inside this housing is the valve actuator. In this case, it's a pilot valve operated by an electric solenoid and air pressure. This small hole is the exhaust vent for the pilot valve. The main parts show up better in this illustration. From the main supply port here is a passage that allows air to flow to this pilot valve. As you can see, it's a two-position, spring offset, three-way valve, such as we described earlier in the lesson. Here's the poppet, and these are the seals here and here. The poppet is spring offset in this position by this spring. In this normal position, the actuator port A is connected through these passages to the exhaust port here. Main supply pressure is blocked. When the solenoid is energized, the pilot valve opens and air can flow through this passage, and supply pressure forces down on the poppet. It moves downward and seals against this valve seat. Now there is a passage from the supply through the valve to the actuator. And as you can see, the exhaust port is sealed off. The four-way poppet valve is essentially two three-way valves, back to back in the same housing, like this. The poppet provides fast response with a minimum of wear because it doesn't have to move very far in order to open up a large flow path. Since it comes apart easily and parts aren't expensive, maintenance costs for poppet valves are low, and the design is resistant to foreign material carried through the airlines. However, it is difficult to obtain poppet valves in some flow path configurations, and in many systems, the crossover flow that is inherent in most poppet valves can cause a failure in shifting. Okay, now let's talk about some things you'll need to know when replacing directional control valves. In order to work properly, the valve must be able to pass the required amount of air to operate the actuator, and at an acceptable pressure. This valve has inlet and outlet ports that are 1/2 inch. This one has ports that are 3/4 inch. Which do you think will pass the most air? Well, this valve here, with the 1/2 inch ports, will actually pass more air than this one. The reason being that different styles of valves will pass different amounts of air. That's why valves are assigned a flow rating, which is usually expressed as a number called the C sub V factor. The higher the C sub V number, the more efficient the valve is. So when you are replacing a directional control valve with a different model, you want to be sure that the replacement valve has as high a flow rating as the one it's replacing. Now, suppose you're involved in designing a system and need to size a directional control valve. How do you figure out the correct C sub V factor to specify? Well, the job is made easier by tables, which are usually available from the valve manufacturer. This one is on page 96 of your text. As you can see, it lists various inlet pressures, compression ratios at sea level, and A constants, which vary according to how much of a pressure drop is allowable in the system. With this information available, you can use a simple formula to calculate the C sub V. The flow rating required for the valve will be equal to the flow rate of the actuator times the appropriate A constant. In most applications, a pressure drop of 5 psi across the valve is tolerable, so you'll usually take your A constant from this column. In critical applications, however, the system may require a pressure drop of only 2 psi. And sometimes a drop of 10 psi is efficient enough for a system, and you can save money and space by choosing a valve with a low flow rating. Here's how to use the table. Suppose an impact tool in a particular circuit uses 10 standard cubic feet per minute at 90 psi. What is the required C sub V factor? Let's say you decide to use a valve with a pressure drop of 10 psi. Then, since the tool requires 90 psi, and the drop across the valve will be 10 psi, you're going to need an upstream or inlet pressure of 100 psi to account for the pressure drop. Checking our table, you'll find that for 100 psi inlet pressure and a valve with a 10 psi pressure drop, the A constant is 0.031. Now, let's just put these figures into our C sub V formula. C sub V equals the flow rate of the tool, 10 SCFM, times the A constant, which is 0.031. The valve will require a C sub V of 0.31 or larger. Now let's size a flow control valve for a circuit with a cylinder in it. The cylinder has a 6-inch bore and a stroke of 25 inches. It is extended at a pressure of 50 pounds per square inch and reaches the end of its stroke in 5 seconds. To size the valve, we need to calculate the flow rate of the cylinder using the formulas we discussed in Chapter 7. First, we find the volume of the cylinder. Then, using the volume, we calculate the flow rate. And when the math is done, we find that the cylinder has a flow rate of 21.6 SCFM. Now we are ready to calculate the C sub V. Let's assume we need a very efficient circuit, so we'll choose a valve with a pressure drop of only 2 psi. Since the cylinder requires 50 psi and the valve has a pressure drop of 2 psi, we'll need an upstream or inlet pressure of 52 psi. So the A factor from the table is about 0.091. Using our C sub V formula, we find that a valve with a C sub V of 1.96 or larger will do the job. Another consideration, the response time of control valves is becoming more important since pneumatic systems are being used more with rapidly moving equipment and often have to provide split-second accuracy in operation. In Lesson 4, we explained that actuator speed, that is, the rate at which a cylinder rod can move, is determined by how fast the cylinder can be filled and exhausted with air. So when a directional control valve is used, it must be properly matched to the cylinder it is controlling. And when a circuit is being planned, the designer will take into account the volume that has to be pressurized and the time it takes to actuate the control valve itself. Generally speaking, where small volumes are to be pressurized, such as on very small cylinders, small ported valves will give faster response than large ported valves. That's the end of Lesson 8. Your review exercises begin on page 101 of your text. I'm Dave Brown for Teletrain.